Today I wanted to talk about phase changes. I think that most of you are pretty familiar with phase changes already, but we'll just kind of go through it. We'll link it to intermolecular forces, we'll link it to entropy, and we'll look at a couple diagrams that help us kind of categorize when phase changes occur, what those phase changes look like, and what's possible with phase changes. So this should be a relatively light lecture as far as like new content and stuff. So hopefully uh, you'll find it interesting and valuable. Okay, so we have six phase changes, really, and you guys probably know most of the answers, most of what all these things are called, right? When we go from solid to liquid, that is, of course, melting. Solid to gas is sublimation. Right? And so when you go straight from solid to gas without stopping at liquid in between, it's sublimation. Liquid to solid is freezing. And liquid to gas is vaporization or boiling. Gas to liquid, condensation. And gas to solid is deposition. One of those that doesn't come up a whole lot, so that's probably the name that people are least familiar with, but deposition goes there. So now in each case, what's happening is we're kind of manipulating, we're manipulating the energy that goes into the system, and we're kind of pitting that energy against molecular forces. So every phase change is all about the energy that's put into the system versus intermolecular forces. And so, again, this is why things like water require much higher temperatures to get to vaporization as opposed to something like methane, which is a similar size, similar weight, similar molecular weight, but doesn't have those hydrogen bonding forces as opposed, it only has dispersion forces, right? So anytime we're going, so when we're going from solid to liquid to gas, right, or solid to gas, right? We can also do that, sublimation, right? Anytime that we do phase changes in this direction, right, we need to add energy to overcome intermolecular forces. I'm going to abbreviate that as IF. Right? So going from solid to liquid, liquid to gas, or solid to gas, what we're doing is these molecules are attached to each other with intermolecular forces, right? So imagine there's a dipole-dipole interaction that's holding this molecule together. As we increase the temperature or put in more energy to the system, what we're doing is we are giving these molecules more kinetic energy. So instead of just in a solid, they kind of just sit there like this. And then as we add more energy, right, we get a little bit more wiggle to it, movement, kinetic energy, right? And then eventually that kinetic energy, the amount of kinetic energy these molecules have becomes greater than the energy of the intermolecular forces. Right? And when that happens, then they start to move past each other and then it becomes a liquid, right? You keep doing it and eventually they stop interacting with each other altogether and then you have a gas. And so what we're doing when we do these phase changes is we're putting more energy in, we're making these molecules move around a lot more. And then eventually they get to a point where they separate from each other, right? And that is the phase change where we go from solid to liquid, liquid to gas, etc. And then of course you can do it in the opposite direction as well, right? Let's say that you're going from um, gas to liquid, right? Condensation, or liquid to solid, freezing, or if you're doing deposition, right? Also possible. In these cases, right, of course, we're removing energy and allowing the intermolecular forces to take over. right? And you can imagine this in the opposite way, right? If you have gas molecules, those molecules are not interacting with each other. There is no intermolecular forces between them. And so as we cool it down, as we remove that kinetic energy, the gas molecules are more likely to collide and kind of stick to each other. They don't have as much kinetic energy. And so then they become, the intermolecular forces get stronger, and we get to a point where we have a liquid. And then so on and so forth. You can keep doing that and end up with a solid. So all these phase transitions revolve around intermolecular forces. The stronger the intermolecular force is, the easier it is for that intermolecular force to take over, and we end up with a liquid or a solid. The weaker that intermolecular force is, the easier it is to overcome, and then we can go from solid to liquid to gas at a lower, without putting as much energy in. So, of course, we can graph all of these phase transitions and where they occur, right? And so when we do that, we have solid up here, liquid in the middle, and then we have gas down here in the bottom. And so each of these areas, right, solid is up here, liquid is in between these two lines. Whoops, I just crossed out liquid, that's fine. And then gas is, of course, down here. Right. So when we do this, each time we cross one of these lines, right, solid to liquid going this way, this is melting. Right, going the opposite direction, liquid to solid, right, the temperature is decreasing. That's freezing. Right? And we can also do this by pressure, right? If you pressurize a substance, you're pushing those molecules closer together. You're increasing the intermolecular forces. And so if you take a gas, where are we? If you take a gas and increase the pressure, right, eventually it condenses and you get a liquid, right? Even though you keep the temperature the same, right? You force those molecules closer together, they start to have stronger intermolecular forces. Eventually the intermolecular forces take over and the molecules start to stick to each other. And of course, you can also do this by temperature, right? We can go from liquid to gas by increasing the temperature, and that is vaporization. And then down here, we do have, in this whatever substance this is, we do have sublimation, which is solid to gas, and deposition, which is gas to solid. So there are temperatures and pressures where sublimation and or deposition can occur. Right? Sublimation and deposition are occurring at this solid to gas boundary right here, where you don't have to go through liquid, right? If you want to go from solid to gas, you can melt it and then vaporize it, or you can just sublimate it and go straight solid to gas. If you reduce the pressure enough, if you reduce the temperature enough, that allows that to occur there. So these phase diagram maps, temperature and pressure, allow us to kind of see where these phase transitions can occur, right? And because we know solid is here, liquid is here, gas is here, we can plug in the various phase transitions that we know anytime we cross that one of those lines that's on there. Okay. There's a couple other things I want to point out. One is right down here where we have all three phases of matter kind of meeting at one point. This is the triple point. Right? This is where three phases of matter can exist, right, at a certain temperature and pressure, right? So in this case, the temperature is about, what is this, minus 10 degrees Celsius, and the pressure is about 6 atmospheres. So if you get there, you can have something that is a solid, a liquid, and a gas all at the same time. Right? So carbon dioxide does a really great job of this. If you can find videos of carbon dioxide at a triple point, and it'll be this weird solid that's kind of melting, but also kind of creating gas and all that other stuff. You also notice that, of course, these stop. The lines stop here. These are the critical points, right? And the critical point is basically always at very high temp and high pressure. And if you get past this point, if you have higher temperature, the molecules just have too much kinetic energy to interact with each other, but the pressure is so high that they're still being forced together. And so the critical points are at high temp and high pressure. Well, in most cases, it's high temp and high pressure. It depends on the molecule. But high temp and high pressure, where molecules are close to each other, have, oops, too much energy for intermolecular forces to take over. And so you kind of have this weird situation where it seems like it should be a liquid because the molecules are so close together, but they all have so much kinetic energy that they can't really interact with each other and have intermolecular forces take over. And so instead of having this liquid, you have this supercritical liquid. You're beyond the critical point, and it has these really weird properties, right? And so critical points are kind of beyond where we no longer have these standard phase 3 phases of matter, right? We no longer have solid, liquid, and gas. Instead, we have these kind of really weird phases where the things that we expect, intermolecular forces and energy and all that, just kind of stops working as well as we would hope, right? And so for the most part, we're going to stay below the critical point because that's where we can make predictions and that kind of stuff in solids, liquids, and gases. Physicists and all of those people are definitely working on supercritical fluids, so they could probably tell you more about what calculations we can make and all that stuff there. All right, I have one last graph to show you, and that will do it for phase changes, and that is this one. So, and this is what happens as we put energy in, right? So as we add energy, right, we notice that temperature doesn't just increase uniformly, right? So you would think that, okay, I put in this much energy, I get this much change in temperature. If I put in the same amount of energy, I should get the same change in temperature. And with phase changes, that's not what we see. Temperature doesn't increase at a constant rate. Right? And so what's happening here where we're putting in more energy, added, no change in temperature. Right? So what's going on there? And what's happening there is this is where our solid is becoming a liquid. This is a phase change. In this case, solid to liquid. But you can see another one in this graph right here would be liquid to gas. Right? So this is also a phase change there. And during that time where all the energy that's being put in, right, up until now, the energy has gone to increasing that kinetic energy for the molecules, right? And so they're kind of wiggling more, they're moving more. During this phase change, what's happening is the energy is only breaking the intermolecular forces. And so, temperature is a measure of the kinetic energy of the molecule. So we increase the kinetic energy of that molecule throughout as we're adding energy. But what happens is that eventually we get to a point where those molecules are ready to separate from each other, right? The intermolecular forces are taken over, or are overwhelmed by the added energy that we're putting into the system. But when that happens, we have to put energy in to break those intermolecular forces because there is those attractive forces of those intermolecular forces are pulling those molecules together. So to overcome them, we have to put enough energy in to separate them. Right? Now that doesn't increase the kinetic energy of the molecules because they're not moving any faster or slower while that's going on. And so that's why we see that kind of flat line at the phase changes. That's where these molecules have moved as fast as they can and still stay a solid. So the temperature is increased as much as it can while still staying a solid. When it comes to a phase change, what we have to do is separate those molecules so that they can now move at a temperature or move at a kinetic energy that corresponds with a liquid. Right? And so when we look at this graph, we see these flat areas, and the reason that those areas are flat is because that's where the phase change is occurring. And that's where the energy is now being used to overwhelm intermolecular forces as opposed to increasing the kinetic energy of the molecules, right? So these slanted areas, the areas that are not flat, right here, the energy is increasing the kinetic energy of the molecules. right? And so we have two different things going on. Right? Sometimes we're increasing the kinetic energy of the molecules. Sometimes we're making the phase change occur by overcoming the intermolecular forces. All right, I think that does it for phase changes. There's a worksheet that kind of very closely mirrors what we're doing here. So definitely check that out. And if you have questions, let me know. Thanks.